Okay, now we would like to talk a little bit about linear regression and discriminant analysis. So for linear classification, LC, linear classification has long been the center of attraction in the ML world. The key reasons are LC, linear classification is in general more effective and highly dimensional feature vector space. LC are essentials for both filtering and wrapper methods in the feature selection. LC also consume less processing time and power during the prediction phase. So the studies of linear classification lay the foundation of the non-linear kernel-based classification. So LC D or L linear discriminating function LDA is a general formulation for linear discrimination function. So LD uh, F right is basically the general formulation and LDA linear discrimination function. So for W equals to W1, 2, 3, 4, 5 to M, uh, encompass E epsilon of Rm, and then X is equals to X1 to Xm to a transpose which encompass R to a power of M when B equals to R and the parameters of this discrimination function. So if W is normalized, i.e. Absolute equals 0, it may be used for projection vector. So you can see the figure for all samples in MR may be projected to one-dimensional space vectors. So hyperplanes are classified in training data where yi equals to plus and yi equals to minus. Yi plus is the green, yi minus is the 0. So it's projected in a 1D subspace, and then in between you see a star basically that is where you can actually exempt this particular space for classification. Um, Objective of linear discriminating analysis given a set say n m dimension vector x x1 to xn the executive LC is to find the linear discrimination function LDF to the best separate two different classes of the training data. So numerous approach of this development LC linear discriminations include the solving of a linear system of equation, maximize separation of margin between two classes, and robust learning model. So with that linear discrimination function, then LDA is a general formula for linear discrimination function. It's a function is equals to W transpose X plus B. So it's more like a functional aspect, and then where W equals to W1 to Wm transpose with epsilon covering from R in the power of M. So that's the full range where X equals to X1 to Xm transpose covering the range of M, and where BR are the parameters of discrimination function. In general, the basic linear systems for regression for learning will be guided by the desired equality W transpose x1 plus b equals to y1, more like explicit function 1 equals to 1 to the power n with x equals to plus 1 for positive training sample, x and y1 equals to minus 1 for negative training sample when m is greater than 1 when there is more notation for unknown and over a determining linear function of an operation. So least square error is a classification by Gauss. The LSE least square error is the objective of a linear regression is best matched to the response F WXI for an input XI to the desired supervised value YI. So WTXI plus B equals to YI. So it's more like a supervised version. So YI will be more like an explicit function. Sometimes what if we put a y function of y-axis will be parametric equation where 1 equals to 1 to n, where I equals to 1 to equals to n. The approximate errors is defined as epsilon is equals to w t which is a transpose xi plus b minus yi. So you actually becomes an implicit function where your arrow equals to 0. The objective of least square analysis is to find the decision vector w and the threshold of b which minimize the following sum square error. So error LSE, a least square error, omega b is equal to summation epsilon square epsilon x plus b minus yi squared. So the optimal solution to obtain by taking the first order gradient of E with respect to b and w and equating them to 0. So hyperclass to classify the training data. So epsilon equals to wt transpose xi plus b minus y is the hyperplane, and then you have plus 1. And then you have also minus 1, which is the green in color, the hyperplane, so that you actually form the decision boundary, which is the blue in color in the center. Yeah. So for optimal solution for LDA, linear distribution, descriptive analysis, we actually could differentiate E to a differentiate E, which is the arrow terms over x, then you actually will lead to b equals to minus omega wt plus b, where mu is equals to summation of x over n is the mass center, where your b is n plus minus n minus or divided by n. So it denotes the centroid adjustment training vectors as x equals to x I minus mu, and you denote the centroid or center scattered matrix as S equals to summation of xi minus mu and mu minus mu, which is equals to xi transpose and x power x transfer. Yes. So optimal solution of LDA is epsilon equals to omega b summation of epsilon square, where summation of et plus b minus y is x transpose of omega plus b minus xi. So denoting the difference of mu plus and mu minus, the power n will give you 2n plus and 2n minus divided by 2, and that will be the change. So optimal solution for LDA is by substituting the equation into 3.3, which will give us the first order of a gradient E omega b with respect to W. So the least square errors will be your 2n plus times n minus divided by n, s minus 1 to the power. So the decision boundary of LSE least square errors classifiers will be equal to W transpose X plus B equals to 0. So the PCA approach is the standardized and the dimensional data set construction of the covariance metric. You decompose the covariance metric into an eigenvalue. Then you set the eigenvalue by decreasing the order of rank to the corresponding eigenvectors. And you select the k eigenvectors from which corresponding to the largest k eigenvalue, where k is the dimension of the new feature subspace. Construct a projection matrix W on top of k eigenvalue, and then you transform the d dimension input data x into the projection matrix W to obtain the new k dimensional feature subspace. So this is a PCA approach. So you basically load on the dimension, and then from a CSV file, you actually has the data frame, a DF, and then after which you could find the least square method using a standard scalar, and you transfer and print it, which is basically to get a final value of it. So the PCA results plot will give you and create something like a PCA class, which applies to the PCA predictor variables, and you see whether you can compact to fewer variables. So basically a PCA is to reduce the fixed variables, and then you result the transformations, you turn the results into array so that you can create a new data, and then you plot the screen as in variance itself into a data frame. So the screen errors, as you can see, if it's more than 8 to 10, you can actually have 100%, but if it's 5, it's actually about 77%. And this example of the container ship data. Yeah. Then the first step is standardize the D-dimensional data set, or you import from sklearn. You basically then standard terms transform, and then the test std you transform. The second step is to come up with a heat map, where heat map equals to SMS heat map data mean correlation, where the maximum value of 1 or some square is true and then not is equals to not true. Step 2 is to construct a covariance metric, where you have a covariance of either x and y, but in this case, covariance metrics could be a covariance of x and a standardization of t. Step decompose the covariance metric into eigenvectors and eigenvalue. So basically, LIN, LRA, LG is a linear algebra package in the Python. Then step 3a is to plot the variance ratio into a principal component. You import matplotlib as a Python plot, and then at the end of the day, you label x and y. Step 4 is to select the k eigenvalue that correspond to the largest case eigenvalue. So you construct a projection of the matrix W from the top of k eigenvectors. Yeah, so that's learn about decomposition. Basically, is to get the k eigenvectors and values. Output variables could be component, experiment variables, explain variance ratio, singular values, and mean. So truncated SDV are singular variation decomposition. Output variable could be component, experiment variables, experiment variable ratios, singularity values, and then the features and features mean. Yeah, so this is the data for the compressors with speed, pressure, etc. And then, yeah, the referencing is like Euler. So that's basically how it actually works. So the appendix theorem is about orthogonal matrix that's transposed from A minus 1 to a transpose, where A is the matrix and the matrix of ATA and AAT are symmetrical. So the matrix of the symmetry is only if the orthogonal diagonalizable. So AT at the end is equals to A. Symmetric matrix is diagonalizable by a matrix of orthogonal normal eigenvectors. So A is equals to EB, ET. And for any arbitrary of m times n x matrix, the symmetrical matrix x and x has a set of orthonormal eigenvectors and a set of associated eigenvalue. These vectors then form orthogonal basis, which the vectors of the length square root of lambda